welcome to problem 5.25. We are going to start by actually doing problem 5.24, so 524, because we are going to use the result of 524 on to do problem 525. All right, so here we see problem 524. Demonstrate the requirement that the first derivative of the wave function be continuous unless the potential is infinite. To do this, we will integrate the energy eigenvalue equation from minus epsilon to plus epsilon and take the limit as epsilon approaches 0 to derive a condition on the difference of the wave function derivatives between two adjacent points. So let's take a look at the wave function, the energy eigenvalue equation. So that is going to be the energy eigenvalue equation as the operator H, which acts on phi of x. And that is then going to be equal to the energy eigenvalue E times the wave function phi of x. So I am going to multiply both sides by dx and then integrate from minus epsilon to plus epsilon. Now, I remember that the Hamiltonian operator, H, is minus h bar squared over 2m, the second derivative with respect to x squared, plus the potential v of x. So let's plug these in, and we're going to move to the next page here. So I'm looking at the integral from minus epsilon to plus epsilon of h, which I now know is minus h bar squared over 2m, second derivative with respect to x, plus v of x, which acts on phi of x dx. And this is equal to the integral from minus epsilon to plus epsilon of the energy times phi of x dx. All right, so I know we can split this up again into a couple more equations. So I'm going to write this as minus h bar squared over 2m. This is going to then be the integral from minus epsilon to plus epsilon, the second derivative of phi with respect to x dx. And then this plus the integral from minus infinity to plus infinity v of x phi of x dx is equal to the energy, because this is just some number, from minus infinity to plus infinity phi of x dx. Okay. So first of all, I can look at this first integral. This is also minus epsilon to plus epsilon, the derivative with respect to x of d phi dx. So my dx's cancel, and I'm left with a little change here so that this becomes equal to the derivative of phi with respect to x evaluated from minus epsilon to plus epsilon, at minus epsilon and plus epsilon. So this is my first useful set of equations. And then I'm going to have a minus sign here. Let's bring this v of x to the other side. So I'm going to have a minus h bar squared over 2m. And then this is going to be the first derivative of phi with respect to x, evaluating at minus epsilon and plus epsilon. This is now equal to the energy time from, and then we're going to integrate from minus epsilon to plus epsilon, phi of x dx, minus the integral from minus epsilon to plus epsilon, v of x, phi of x dx. So I am going to now multiply the whole thing by minus 2m over h bar squared. Okay, so looking at this, I am now just going to get the derivative of phi with respect to x, evaluated at minus epsilon and plus epsilon. This is now equal to, the minus signs here on the right are going to cancel, so I'm going to write this term first. This is the integral from minus epsilon to plus epsilon, 2m over h bar squared, v of x, phi of x, dx, minus 2m energy over h bar squared, the integral from minus epsilon to plus epsilon, phi of x, dx. So we say, that's nice. Now, let's write out this one just a little bit more. So this is the derivative of phi with respect to x, and we're going to evaluate this at plus epsilon, minus the derivative of phi with respect to x, evaluated at minus epsilon. This is equal to 2m over h bar squared, the integral from minus epsilon to plus epsilon, v of x, phi of x, dx. I should state that this whole derivation is assuming that the point of interest we care about is x equals 0. If it's not, then it becomes whatever point you're interested in plus or minus epsilon. So maybe a minus epsilon and a plus epsilon, if you're interested in the point x equals a. Minus 2m energy over h bar squared. This integral from minus epsilon to plus epsilon, phi of x dx. Okay, so what we're going to do next is we're going to take a limit of this whole thing as epsilon goes to 0 of the following mess. So we don't know anything about v. V could be going to infinity. We don't know. We don't know anything about these derivatives, if they're the same or not, but we do know is that phi is continuous. Phi must be continuous, which means that regardless, as epsilon goes to 0, this entire integral goes to 0, because I'm just evaluating phi right at that point, which must be continuous. So there must be no difference as this gets infinitely small. So I am now left with the following condition: the derivative of phi with respect to x plus epsilon minus the derivative of phi with respect to x evaluated at minus epsilon is equal to 2m over h bar squared times the integral from minus epsilon to plus epsilon, v of x, phi of x, dx. All right, this is the answer to problem 224. So let's go then to problem 525, which is the one that we're actually interested in. Here we have a potential v of x, and they tell us that v of x is equal to minus beta times delta x, where this is the Dirac delta function. And beta is a positive real constant. Although, I mean, once you know positive, I'm not really sure you need to know anything else. So that means that this is a potential that goes down into the negative region. So coming along here, and then go with sound effects. It's better with sound effects. But you can see that the potential goes down this way, and the Dirac delta function is defined that it goes to infinity at x equals 0. And so this is v of x. but it also goes to infinity in such a way that when you integrate it, you get 1. So what I'm going to do is I'm going to apply this to my conditions so I can figure out what the conditions need to be, because I know this goes to infinity and I don't know really anything else useful. So let's look at integrating from minus epsilon to plus epsilon, v of x, which is minus beta delta of x, phi of x dx. Say that's nice. The minus beta comes out, and I am just left with minus epsilon to plus epsilon delta x phi x. So you may or may not remember that when you integrate delta x, that it is 0 everywhere except when this inside the parentheses equals 0. So this means that this is minus beta, and I just evaluate the rest of the function at x equals 0. So this is phi of 0, and that's it. That's what it's equal to. So if we look at this point, v of x, here's x, and then here is the potential. I can think about having 2 regions, region 1 and region 2. In these 2 regions, in these 2 regions, v of x is 0, and so I just have minus h bar squared over 2m times the derivative with respect to phi, second derivative with respect to phi, equals the energy times phi. So this tells me that I have the second derivative of phi with respect to x squared, and this is minus 2me over h bar squared times phi of x. Now, one thing to note here is that we are interested in the bound states where E is negative. So these are the trapped states here. We're not interested in any of the states that might be up above, that have energy greater than 0. That's the next chapter, chapter 6. Right now, we're interested in what might be caught in the well. So we're going to assume E is negative, which is a reasonable assumption for that. And I'm then going to say, let Q squared be equal to minus 2m times E, which is negative, over h bar squared. So this whole thing is actually positive. So I then have this derivative with respect to x squared equals q squared phi, curly phi. So this gives me then a solution which is phi of x equals a e to the qx plus b e to the minus qx. All right, let's look back at our potential again. This picture is getting worse and worse. Region 1, region 2. So region 1, x less than 0. I still want phi to go to 0. So I'm going to write down my general solution here. Phi of x is equal to a e to the qx plus b e to the minus qx. This is an x. So I want to make sure that this doesn't blow up. So that means I'm going to keep just the first term. So this, what I'm going to call, let's just call this phi 1 of x. This needs to be equal to a e to the qx. So this term, remember q is positive, x is negative, and as x as x goes to negative infinity, phi 1 will go to 0. So that's good. We don't want this blowing up anywhere, which is reasonable. In region 2, which is where x is greater than 0, then we have phi 2 of x. This is just going to have, I need to have the exponential decaying term, so minus q of x. So again, as x goes to, this time, positive infinity, I want my wave function to be decaying towards 0. So I need to have the minus sign out front. So this helps quite a bit. And I can use this useful piece of information going forward. So I did look, and previously we applied our condition, which was the derivative of phi with respect to x evaluated at plus epsilon minus the derivative of phi with respect to x evaluated at minus epsilon was equal to 2m over h bar squared, the integral from minus epsilon to plus epsilon of minus beta delta x phi of x dx. And we determined that this was minus 2m beta over h bar squared times phi of 0, whatever that is. And then I know what these, I can look at these derivatives. This is the derivative from the positive side, that's region 2. So region 2, and this is region 1. All right, so phi of 1, which is when x is less than 0, is equal to b, is equal to a e to the qx. And phi 2, which is when x is bigger than 0, this is equal to b e to the minus qx. At 0, I need this to be continuous. So phi 1 of 0 is equal to a, and phi 2 of 0 is equal just to b. So this means that these two need to be equal. So a equals b. So I'm going to write this one as a e to the minus qx. So if I take the derivative, whoops, of phi 1 with respect to x, that is the derivative with respect to x of a e to the qx. And then I'm going to evaluate it at negative epsilon. So this derivative is a e to the qx times the derivative of the stuff inside, which just gives me q, and evaluate at minus epsilon. And this then becomes a times q e to the q minus epsilon. All right, so this is the derivative of phi 1 with respect to x evaluated at minus epsilon. I can then look at the derivative of phi 2 with respect to x, which I will evaluate at plus epsilon. So this is going to be the derivative with respect to x of a e to the minus qx evaluated at plus epsilon. And this is going to be equal to a e to the minus qx times minus q evaluated at plus epsilon. So this is minus q times a e to the minus q epsilon. So let's look back at our condition, which was the derivative of phi with respect to x plus epsilon minus the derivative of phi with respect to x minus epsilon. This was equal to 2m over h bar squared, the integral from minus epsilon to plus epsilon, v of x, phi of x, dx. So far, we'll plug in this one. This is minus q times a e to the minus q epsilon minus, this one was q times a e to the minus q epsilon. And this is equal to, oops, minus 2m beta over h bar squared, phi of x at 0. So phi of 0. But phi of 0, remember, this is just equal to a times e to the 0, which is just 1. So I have minus q a e to the minus q epsilon plus q a, oops, minus q a e to the minus q epsilon, which is equal to minus 2m beta over h bar squared times a. For which there is much rejoicing, because this means that all the a's cancel. Woohoo! Which is good, because I didn't know what they were anyway, so that's convenient. So this gives me minus 2 times q e to the minus q epsilon, which is equal to minus 2m beta over h bar squared. So say, okay, then the 2's cancel, the minus signs cancel, and I am left with q equals m beta over h bar squared e to the plus q epsilon. Now, remember, I care about this. What happens as epsilon goes to 0? This is the limit that I care about. As epsilon goes to 0, e to the q epsilon goes to e to the 0, which is just equal to 1. So in this limit, q is equal to m beta over h bar squared. I say, oh, this is fantastic. So here, q equals m beta over h bar squared. Does anybody remember what q was? Well, if we look back, this is minus 2m times the energy over h bar squared, which I'm going to take the derivative of, and this is equal to m beta over h bar squared. So remember that e was negative, right? I'm going to square both sides, so I get minus 2me over h bar squared, and this is equal to m squared beta squared over h bar squared times h bar squared. So one unit of the h bar squares cancels, one of the masses cancels, and I am left with minus 2 times the energy equals m beta squared over h bar squared. Or I can solve for the energy, which is equal to minus e beta squared over 2 h bar squared. This is the energy of, and there's only one energy, so this means that there is one bound state. And it has this amount of energy, whatever that is. Yes, so that's the answer to our question. The question here was, how many bound states are there? And the answer here is there's one bound state. I would write this as one bound state with an energy of minus m beta squared over 2 h bar squared. So you will be doing the next problem, 526, that has two delta potentials. using these same principles to figure out how many bound states are in that one.